Hi, my name is Charles. I'm the product manager for Piezo at CTS, and today we're going to talk about lead-free piezoelectric materials. To start with, we will look at the RoHS regulation and the background for working with these lead-free materials. And then I'll give some details about our commitment and activities within the field of lead-free, to finally move on to our lead-free materials that we are launching today. We have a wide range with different properties, so we're going to have a quick look at that and then look at the different applications where these materials can be of use. And then my colleague Baltra is going to present a case study about the replacement of PZT by KNN in a flow transducer. And after that, my colleague Vojtech is going to present a comparison also including KNN and NBT-BT in a power transducer. In the end, we'll just do a short summary. So first about the background. We have this RoHS directive, which is driving the activities in the lead-free field. Piezo has been exempted, and if you refer to the directive currently, it says the exemption expires in July 2021. That is because the directive still hasn't been updated. There is a report from an expert panel that was commissioned by the European Community to extend this exemption to July 2026. So we are expecting this to be updated, but we are of course exposed to further exemption in the future. So there's of course a great interest into developing alternatives to lead in piezoelectric ceramics. And this is of course something that CTS has been following and working on. We've had developments for over 20 years at our ferroperm facility in Denmark. And this is something that we highlight also in our ESG report that we published last year. And in the end, we participated in a number of research projects. We did dissemination activities. You might know our Innovation Hub webinars that are linked also on this YouTube channel. And finally, we've launched our range of lead-free materials, which is highlighted in our Piezo brochure, a component brochure, and also we issued a specific lead-free brochure with all the materials in comparison. And when I say all our materials, we are talking about materials that have been developed over the past years, and some of them have just hit production, and these are the materials that we are launching. We have we've had lead-free materials in our catalog for some time. Actually, we've had high temperature materials that I'm going to talk about in the next slide. But we've also worked on KNN-based materials, NBT-based materials, and we're still working on some, let's say, next generation lead-free materials. We have projects ongoing with textured KNN materials and gadolinium doped cerium oxide, which are not ready to hit production yet, obviously, but they are in the pipeline. So what we are going to talk about today is these materials that are ready and are hitting sampling stage, and that would be available for customers. Going into more details about different materials, I'm going to start with the bismuth titanate based materials, which are also called bismuth layer structured ferroelectrics. And these are very non-isotropic materials, and you can see the structure here in platelets. And their advantage is really the very high Curie temperature. We have Curie temperatures in the 600 to 700 degrees Celsius, and that means that we have a material that is very stable with regards to temperature, and also with regard to field, so electrical field. So a low loss material, high field capability, high temperature capability. And also because of the structure, we have high anisotropy. So the thickness coupling is much superior to the planar coupling, which is an advantage when you're developing a thickness mode transducer. In addition, we have a material that has a very high quality factor, mechanical quality factor, which means it can be used for resonant applications. The drawback of these materials is that the coupling, or more precisely the sensitivity, so the piezo coefficients are relatively low. So this needs to be taken into account. We have two materials in that range, PZ46, PZ48, with different Curie temperatures. Another class of materials is sodium bismuth titanate, barium titanate materials that we call NBT-BT. So we have a base of NBT where a barium titanate content was introduced to enhance the properties. The main advantage of these materials is that they can resist high vibration velocities. They are also relatively anisotropic. Like I mentioned before, the thickness coupling is superior to the planar coupling, which is an advantage when designing a thickness mode transducer. But the drawback of these materials is the relatively low depoling temperature. Sensitivity is higher than the bismuth titanate materials, but still behind the PZT materials. We have two materials in this range, PZ12 and PZ12X, with different properties in terms of coupling and dielectric factor. Finally, the third family of material that we're going to talk about today is the potassium sodium niobate based material called KNN, more commonly. And it's a very popular range of materials simply because the properties can be tuned just like we do with PZT by adding dopants. So we have materials that can reach high sensitivities, so high D coefficients, and that can also be tuned in terms of the mechanical quality factor. So we can basically cover the whole range with that family of material. A common feature of these materials is that they have a relatively good temperature stability. We have Curie temperatures that are comparable to what we know from PZT. And also they have low acoustic impedance, which is an advantage when designing transducers that are coupled with water, for example. On the other hand, we do have to compromise on some of the properties, and we're going to see in the other presentations what it means from a transducer perspective. And like I said, we have a range of these materials. Some would be more comparable to soft materials, or soft PZT materials like we know them, and some can handle the high power and power applications. Now I've selected some properties here in that table for your reference. All the data is available in our material data sheet, and that is online, so please take a minute to review it. What I just wanted to highlight here is that we have materials that cover quite a wide range of properties. We have materials with high mechanical quality factor, QM, that are applicable for power applications. We have materials with a low QM for mostly sensing applications, and then we have materials in between. So we can cover quite a wide range, also in terms of dielectric constant, from the, I would say, very low dielectric of the high temperature materials to relatively high dielectric here for LF41. And the same applies to most of the properties. We can cover a very wide range Like I mentioned, we have very high Curie temperature for some materials, and we have temperatures in the range that we are used to with PZT for the KNN materials like PZ62, for example, in the 300 degrees range. Properties vary quite a lot, and you see here in terms of coupling that we have very different values from the very low planar coupling of the high temperature materials to relatively high planar coupling for LF41, and the same for thickness coupling Kp, which goes up to 49%, which is quite a decent value for piezo material. All right. Frequency constants are very different. This is something you need to keep in mind when designing a transducer and designing a product. This is very different from PZT materials. And the same for acoustic impedance. So this needs to be taken into account. In the end, we offer these materials, and we believe they cover quite a wide range of applications. So this is just a very brief application matrix where you can see, according to your application, what materials we would recommend. And basically, there is a material for each application, and we can help you with the design and the recommendations. Now I'm going to leave the floor to my colleague Baltra, who is going to present a case study on the replacement of soft PZT by KNN in the flow transducer. Baltra, the floor is yours.
Thank you. Thank you for a great presentation and introduction. Hello, everyone. Thank you for joining our webinar. Now I will present the design, testing, and comparative analysis of lead-free KNN NTK type and PZT piezoceramics in the time-of-flight flow meter application. Before jumping into the technical things, let's discuss our agenda. So firstly, I will start with a brief introduction of our objectives and the background of the study. Then we will jump to direct replacement of lead-containing ceramics in time-of-flight flow meter application. We will see how it can be approved while providing finite element analysis and comparing experimental results. We will wrap up everything with brief conclusions. So the main goal is to evaluate lead-free KNN type piezoceramics suitability in industrial applications compared to traditional lead-free based PZT materials. The background, as already my colleague Charles mentioned, is mostly RoHS compliant with at some point wants to eliminate all the lead in electronic and electrical devices. So this compliant sparked a growing interest in alternative lead-free materials, and of course CTS also joined the train. So CTS conducted a comprehensive comparison between PZT material NC51 and lead-free material LF41. And as you can see from relative differences of each property, unfortunately, lead-free material seems to be weaker in the application. However, there are a few advantages, like the electric constant, which is higher. That indicates that in the final application, the capacitance of the fly of time transducer could be higher. Another advantage could be density. Because of the lower density, the lower acoustical impedance should be acquired, and which means better element matching with the fluids which is required in this application case, and just a better effectiveness of energy transfer. So later we will see if it's enough to match the PZT material in performance or not. Jumping to the properties comparison, we did two comparison between the lead-free material and lead-based material NC51, and we compared it with on-scale performed simulations to acquire models for further investigation. On the left, you can see LF41 material matching quite well with finite element analysis data, and this was tuned by with the cooperation of on-scale team, so it's matching quite well. And on the right, you can see the measured curve and the finite element analysis curve of NC51, which is not matching perfectly due to some small inaccuracies in damping and matrices. As going further into the thickness mode and higher frequencies, we can see a bit more mismatching due to, again, as mentioned before, inaccuracies in material matrices in the software, and also due to the damping of the material while measuring the pieces. However, both curves show that our values required for the sensor are in the range of 2 megahertz plus minus 5%. So either parts and the models are qualified for further investigation. Before jumping to the design of time-of-flight flow meter, it is necessary to understand the main working principle of this transducer. So basically, a pair or more transducers are required in this application. One of them generates and another senses ultrasonic wave and vice versa. And the time of flight difference with and against the flow is directly proportional to flow velocity. Now that we are familiar with the working principle, let's jump to the design. From the first glance, the design doesn't look really difficult. We have wire, we have backing layer, we have casing and active element. However, in general, it's not so easy because we need to ensure uniform layer of glue. Also, the parallelism between the casing and the active element to achieve the best energy transmitted as possible. And of course, the thickness of the casing to match for acoustical impedance between the materials and the fluid, which where the part will perform. Going further, two finite element analysis models were created. The first one was done to evaluate the impedance response of the subassembly, and another one was to evaluate overall performance of the time of flight transducer in the fluid. So the first model, as you can see, is both models, as you can see, are without a backing part to reduce the complexity of the simulations. So the most important parameters were the driving frequency, it's 2 megahertz, where the best energy transmission is achieved, and the mesh, which should be at least 15 nodal elements per wavelength. Here you can see a short video of our simulation of 20 pulses excited in the piezoceramic, reaching the steel mirror and reflecting back to our transducer. Jumping to the results. From these tables, from these graphs, we can see already the evaluation between NC51 and LF41 materials in the FEA model and the real assembled cases. So from there, we can see that simulations showed 26.6% difference in the performance. And in real cases, lead-free material was weaker by 35.5% overall. Knowing that, CTS team started to brainstorm how we could achieve a better performance of lead-free transducers, and we came up with some ideas how we could do it. But unfortunately, it seems all of them have some drawbacks. So the first one is just changing the backing layer to less damping material. That would probably achieve better performance. However, we are reducing environment resistance in the final application. Another is to reduce the thickness of matching layer by half of weight length. However, it would reduce overall strength in the final application with the possibility of damaging the sensor. And the third one was to increase the active area. However, it would increase the size and the cost of the transducer. So our team decided to continue investigating the third case. And let's jump straight to the results. So basically, we increased the diameter from 7 millimeters to 9, and we did the same way to evaluate the performance. And here already we can see that diameter 9 lead material and lead-free material are compared, where we have quite similar difference in the simulations, which is approximately 37%, and in the real assemblies, we got quite matching difference in the overall performance of transducers, and lead-based material was lower by 34%. So jumping to the results, there are two things that probably I should mention. That simulation results showed a bit higher performance of the transducers compared to the real cases due to perfect conditions in the simulations. And another important thing, that increasing the active area of element by 23% got us 2.7 times more performance in the final application, and also increased significantly the capacitance, which is also important parameter for this transducer. And following that, and wrapping up with conclusions, LF41 material exhibited much lower overall transmitted energy compared to PZT, which is approximately 32%. However, increasing area by 23%, we managed to increase the performance by 2.7 times. And leading by that, we can say that KNN NTK type can reach and even exceed the performance of PZT, however, with compromise in robustness, dimensions, and other transducer properties. Thank you for your attention.
Thank you, Baltra, for a great presentation. Now we have a contribution from Vojtech about the replacement of hard PZT by KNN and NBTBT in power transducers. Vojtech, it's your turn.
Hello, everyone. My name is Vojtech Hruby, and I work as a research and development engineer at CTS Corporation. And I will present to you a study we did on the topic of PZT replacement by lead-free materials in ultrasonic power application. First, I will introduce this study. I will show a BLT transducer, which we used to compare the materials, and also the materials we used. Then I will move to, I will show impedance measurements we took during important assembly stages of the transducer, and I will show nodal point position problematics. After, I will move to high power driving results, the method we used, and the results we obtained with it. And finally, I will discuss and summarize the results. So as already my colleagues showed or discussed, there are environmental concerns about lead, basically, which is contained in PZT. And so there is need to move towards lead-free solutions. In this study, we compared PZT material and two lead-free alternatives as a part of bolted Langevin transducer for handheld medical applications. And the aim of this study was to define the challenges connected with PZT replacement by lead-free materials and to provide a baseline for a comparison of these materials in ultrasonic power application. Bolted Langevin transducer enables high power generation at relatively low frequencies, and this is possible due to the longitudinal vibrational mode of the whole transducer structure. Bolted Langevin transducer consists of front and back mass made from metal and from central bolt, which is used to preload a piezoceramic stack in the middle. Most of ultrasonic handheld surgical devices operate in frequency range between 20 and 70 kHz, and they are used for hard and soft tissue cutting tools, tools for cataract surgery, or for dental scalers, tools for liposuction, etc. In this study, we used a CTS transducer, which was designed for handheld surgical applications. It uses 4 piezoceramic rings of OD 14 mm and thickness 2 mm, and operational frequency of the transducer is located around 50 kHz. In this transducer, we tested 3 materials. First one was PZT material, that was NC81, which is low-loss Navy Type 3 PZT material, intended for power applications, which require low losses. Then it was PZ12 material, which is CTS lead-free NBT-BT type material, and it is intended for general purpose applications. Then we have LF52 material, which is CTS lead-free KNN type material, intended for power applications, and again it has low dissipation, so it can be thought as a lead-free replacement for NC81. If we look into selected parameters of piezoceramic materials we tested in this study, we see that PZ12 material has much higher losses, and that is the tangents delta and mechanical quality factor. Also, if we look into the acoustical properties of materials, we see that both lead-free materials have a much higher speed of sound and a lower density than PZT material. So that affects some behavior of the transducer. Also, we need to mention that these material parameters are calculated at low signal levels. So behavior at high power levels or high driving levels can be different. And this is also why we conducted this study. We preloaded transducer in steps, and we measured impedance response, and then we did some charts, and these charts we show here. This is dependence of impedance magnitude at resonance on the preload, on the applied preload. So on the left, you can see a PZT transducer. In the middle, you can see PZ12 lead-free transducer, and on the right, you can see LF52 lead-free transducer. And we will keep this organization of the charters through the whole presentation. So always on the left, there will be PZT, in the middle, PZ12 lead-free, and on the right, LF52 lead-free. So you can see that the trend is same for all three materials. Impedance magnitude at resonance is decreasing with applied preload, and this shows improvement on the mechanical contacts formed between transducer parts. If we look into the dependence of resonance frequency on the applied preload, we see that the trend is also same for all three materials. Resonance frequency is increasing with applied preload. And the change is greatest for the PZ12 material. So we can see that there is a really high change in resonance frequency as the preload is increasing. So after we preloaded transducer, we did a stabilization procedure, which is basically thermal treatment. And this is done to prevent rapid aging of the transducer in the transducer lifetime. You can see that the difference between resonance and anti-resonance frequency, which corresponds to effective electromechanical coupling coefficient, is much higher for the PZ3 transducer and lower for lead-free alternatives. Also, you can see that the final impedance magnitude at resonance is really different among these three transducers. And it is 6 ohms for the PZ-T transducer, and then 270 ohms for the PZ-12 lead-free, and 60 ohms for the LF52 lead-free transducer. We also did FEA simulations of the transducer, and in this case, it was relative displacement at resonance frequency, and we did this to allocate the vibrational node of the transducer. In the right, you can see a comparison of three transducers, and you can see that there is clear shift of the nodal point on the lead-free versions. And if we let's say summarize, or if we let's say state what is the optimal position of the node. So typically this is at the nodal flange where transducer is clamped, or at the position of PZ-T stack to give some, let's say, maximum performance of the transducer. So if we look at this ideal position, then we see that on LF52 transducer, the nodal point is off the optimal position. So if we proceed to high power testing, we prepared a test bench to test transducers at high driving levels. This test bench was consisting of a laser Doppler vibrometer, which we used to measure vibrations amplitude at the tip of the transducer. Then we incorporated thermal camera to monitor transducer stack temperature. And we drove transducers at resonance frequency to reach specific displacements. So we prepared 3 driving scenarios. First one was ±1 micrometers displacement. Second one was ±2 micrometers displacement. And third one, ±3 micrometers displacement at the transducer tip. And we drove transducers over 15 minutes, or until temperature of the transducer stack reached 70 degrees Celsius. As you see, a transducer was clamped using 2 O-rings, was clamped in between or inside the fixture. So at first driving scenario, which was ±1 micrometers displacement, we can see that there was really negligible heating on the PZ-T and LF52 lead-free versions. These charts shows evolution of transducer stack temperature over time. And so with PZ-12 transducer, you can see that the transducer was already heating and the temperature was stabilized around or between 40 to 45 degrees Celsius. From this, it's clear that PZ-12 transducer has much higher losses, as the transducer stack heating is a loss indicator. And the charts below, they show relation between transducer stack temperature and input power. So you can see that the PZT transducer was consuming less power than the lead-free alternatives. Moving to the second driving scenario with ±2 micrometers displacement amplitude, we can see that already all transducer solutions were heating, or all transducers. PZT and LF52 versions, the temperature of the stack stabilized between 40 to 52 degrees Celsius. And with PZ12 transducer, the transducer was heating really fast, and the 70 degrees temperature of the PZT stack was reached between 6 to 11 minutes. If we look into the input power, we see that lead-free transducers consumed more or consume more input power to reach the same displacement. And in case of PZ12 transducer, that was approximately 2.5 times more power, and in case of LF52, it was approximately 1.5 times more input power. Also, we can see that with increasing temperature, the input power is dropping on the lead-free versions. So moving to final driving scenario, which was ±3 micrometers displacement. So in this case, we only tested LF52 and PZT transducers. And this was because PZ12 transducer, the lead-free one, was heating too fast. So it wasn't really a point to measure it in this scenario. And we see that the PZT transducer reached 70 degrees between 10 to 15 minutes. And with LF52 lead-free alternative, we reach 70 degrees between, let's say, 3 to 6 or 5 minutes. So from this, we can see that still lead-free alternative has higher losses than PZT version, although the performance is quite good. And if we look into input power, we again see that we need approximately 1.5 times more input power to reach the same vibration displacement amplitude. So to discuss and summarize, we see that direct replacement of PZT by lead-free material in existing ultrasonic bolted Langevin transducer is possible if some trade-offs in performance can be accepted. Due to different acoustical properties of the materials or of the lead-free materials when compared to PZT, resonance frequency of the transducer changes and also nodal point shifts. So this is important to consider. Significant difference of resonance frequency and also impedance magnitude at resonance requires some adjustments in driving systems. Also, due to higher conversion losses, more power consumption of the transducer and faster heating can be expected when it comes to lead-free alternatives. It is important to mention that in this study, we didn't optimize the lead-free transducers. And so for optimal performance of these adjustments or optimization, tuning redesign is needed. This means in general adjustments on transducer dimensions to keep optimal resonance frequency and also optimal nodal point position. Increase of piezo ring size, this means mainly diameter, might be required also to compensate for lower power density of lead-free materials. Thank you for your attention.
Thank you, Vojtech. Very interesting. So, well, thank you again both for your inputs. We've seen that CTS can offer a wide range of lead-free materials. We have materials with high performance that come close to PZT for certain applications. And of course, it is the same challenge as with the initial design of a transducer. With the PZT, you need to know what's the most appropriate material for a given application. So it's really going back to, I would say, square one into selecting the right material for a given application. We have these lead-free materials that offer specific advantages, such as low density, the low acoustic impedance, the high temperature capability, and the high anisotropy, for example, which can provide some specific advantages for niche applications. However, in many cases, there will be some compromise. It is not a one-to-one replacement. And as both Vojtech and Baltra mentioned, there is some level of redesign that is required. So basically, you can achieve the same performance, but with a trade-off on some other properties. It may be at the transducer level, changing the dimensions to reach the same performance, adjusting the weight repartition to maintain the position of the nodal points, and so on. But it could also be on the driver side with all the differences that we've seen in terms of impedance and driving signals. So these are important aspects to take into account when redesigning your application with the lead-free material. In any case, CTS is here to help you, so don't hesitate to contact, and thank you for your attention.